Okay, so here's going to be a brief review of the circular motion. So to begin circular motion, we'll start by talking about uniform circular motion. So think about what it needs to be uniform circular motion, right? So uniform circular motion is when we have a constant speed, right, throughout the entire path. So that tells me it's a constant speed. Now be careful when you're referencing uniform circular motion that we are thinking constant speed and not constant velocity, right? One of the first things to make sure we are comfortable with is if we are moving in a circle, right? If I know that I'm moving in a circular path, I know that there has to be an acceleration, right? There has to be an acceleration going towards the center of the circle. So if I'm moving through a circular path at a constant speed, there's got to be a centripetal acceleration. They do give us that definition on the equation sheet. They define the centripetal acceleration as v squared over r. We can make a quick extension of that and realize then that the centripetal force, which would simply be mass times the acceleration, so mass times v squared over r. This one is not technically on the equation sheet, but hopefully is easy enough to get to, right? And then conceptually, we have to make sure we're comfortable with the fact that, again, why does it have to have an acceleration, right? So the definition of acceleration is change in velocity, right? So why, if I'm going around a circle at a constant speed, do I have to have an acceleration? Well, the answer to that is the fact that the velocity, which is tangent to the circle, is changing directions, right? So we have to have a centripetal acceleration because there is a change in the direction of velocity. And so as the direction of velocity is changing, then that means velocity is changing. And so since there's a change in velocity over time, there has to be an acceleration, which also means then there has to be a force causing that acceleration. So those are some big concepts that we need to realize, right? In order to move at a constant speed around a circle, we do have to have an acceleration with that. We do also want to consider when is it just centripetal acceleration versus also tangential acceleration. If it's uniform circular motion, then the tangential acceleration would be 0 because that means that we're not speeding up as we go around the circle. So that tells me that there is no tangent acceleration, right? Because if there were a tangent acceleration and I was moving this way, well, if I move and accelerate the same direction, then I should speed up. But since uniform circular motion is constant speed, there cannot be any tangential acceleration if and only if it's uniform circular motion. So that is something else to consider. So if they ever asked us to find the total linear acceleration, we know that normally linear acceleration comes from both centripetal and tangential, but if we're talking uniform circular motion, there is no tangential acceleration. Okay, one of the other equations that's very helpful for uniform circular motion that is not on the equation sheet, but is again very helpful anytime I'm dealing with a constant circular motion, is just v equals delta x over t. We know that for a constant speed or a constant velocity, we would use delta x over t. Now, in the context of a circle, we know that the distance that we travel as we go through one circle would be the circumference, so 2 pi r, and the time for exactly one cycle is what we refer to as a period. This is a huge equation when it comes to circular motion, and making sure that we keep it simple and we focus on the basics. But as long as I can either find or measure the radius, and as long as I can either find or record the time, I could then pretty easily find my velocity if I needed it. So again, a big equation that is not on our equation sheet, but is very helpful when we have centripetal motion going on or circular motion going on. And then conceptually, probably the biggest thing on most of these questions. So again, I know if I'm moving in a circle, I know right now that there has to be an acceleration going towards the center of the circle because my velocity is changing directions. Therefore, there has to be an acceleration going towards the center. That also tells me, again, if it's uniform circular motion, the net force must be directed towards the center of the circle. And that is because the net force is our centripetal force, right? So when you hear centripetal force and when you think about centripetal force, we need to realize that centripetal force is not its own thing. Centripetal force is just whatever force happens to be going towards the center of the circle. So the number one thing that you should try to identify on any question where we're moving in a circle, the number one step is maybe do a free body diagram and figure out what forces are providing the centripetal force, right? Is centripetal force coming from maybe tension? Is it coming from maybe a friction between a horizontal road surface and the car itself or whatever it may be? Is centripetal force coming from gravity, right? Is it coming from some combination of these, right? Maybe it's coming from a combination of multiple forces. And so I'll run through a few of those examples because that's really where this section gets important, is deriving some of the equations, finding some of the equations based off of what centripetal force is coming from. So let me start with kind of a simple example for, let's say that I have a ball on the surface of the Earth, and I'm taking that ball and I'm swinging it around in a vertical circle looking something like that. So as the ball is going around in a vertical circle, so I'm swinging it basically up and down, right? At the highest point, we know that the string would be straight up and down. At the lowest point down here, if I was doing it at this point, we know that the string would be, again, straight up and down, and that either to left or right sides, the string would be pulling directly towards the center. Let's think about what the centripetal force would look like at either the top or the bottom. So I'm going to call point 1 the top. I'm going to call point 2 the bottom. So at the highest point, we know that there has to be a centripetal force going towards the center of the circle. Again, the first step there is just to think about what forces would be acting on the ball at the highest point. Well, if we have tension, it's pulling down, because that's the way that the string would pull, right, is along the string. So tension might be pulling down, and we know for sure, if it's on the surface of the Earth or any planet for that matter, there has to be a force of gravity pulling down as well. Now, those two forces are both directed down, and together they would be making up our centripetal force. So once again, keep in mind that centripetal force does not belong on the free body diagram. It does not belong on the free body diagram because it's not its own force. However, if I treat this like any of the pulley questions we've seen before, I can set up a net force equation for the centripetal force, where centripetal force would equal a combination of both the force of gravity and the tension. And since they are both pulling down in the same direction as the centripetal force would need to go, we know it needs to go downward if it's at the top, then I'm adding those two together. At the lowest point, tension would be pulling upward, gravity would be pulling downward. Be very careful at the lowest point. It's almost second nature sometimes to say, well, those two forces have to be equal and opposite. They don't have to be equal and opposite though, right? They can't be equal and opposite, because if they were, the net force would be 0. If the net force were 0, we would not be accelerating. And if we weren't accelerating, we cannot move in a circle. So instead, we know that the net force has to be going towards the center of the circle, because otherwise I'm not moving in a circle. So at the lowest point, tension's pulling up, gravity's pulling down. We know that the net force, the centripetal force, has to be going towards the center of the circle. So the equation I can set up for my net force would look something more or less like this. My centripetal force is going upward. Tension is working with me, pulling upward. My force of gravity is working against me. There I've got my relationship at the bottom of the circle. So again, this is just kind of a generic question where maybe I'm identifying what forces provide the centripetal force. There is a specific concept that ties to vertical circles, and that concept is what we called the critical velocity when we saw this in class. The critical velocity represents the minimum speed needed to maintain a vertical circle. So if you think about it, if you were to swing something very slowly around the circle, if you swing it just slow enough, then it just barely stays in the circular path at the highest point, right? At that highest point, you can almost see the slack in the string as you're swinging around, and that object just barely stays at the top. That's the idea here of critical velocity. So critical velocity comes from the fact that at the highest point, there's always a force of gravity, but if we're going at the very minimum speed, we actually don't need any tension at the highest point, and we allow gravity to provide all of the centripetal force for us. So the key then to the derivation and the finding of our critical velocity is by simply identifying that the centripetal force comes from only gravity at the highest point in the circle. Well, since centripetal force is calculated as mass times velocity squared over the radius, and since the force of gravity is mass times gravity, in this case, both of those masses are the same because both are indicating the mass being acted upon. So the mass cancels out for each of those. I can multiply both sides by r. I get v squared equals r times g. And then v equals the square root of r times g, or gr. That represents our critical velocity, right, for a circle that's being swung in a vertical circle on a planet. So typically if it's Earth, I'm going to use 9.8, right, unless they're telling me something otherwise. If it's a different planet, maybe I have to find the acceleration and gravity first. But it's an easy enough equation to use. The important thing is we need to know what it represents and probably even more importantly, where it comes from. So knowing that derivation, again, very important for us to be able to do. Hopefully that makes sense. Again, definitely something I would encourage you to run through this one a few times on your own. Make sure you feel confident with it. And most importantly, make sure we know when it applies, right? A similar equation is when we start talking orbit. So we actually have two equations that emerge from our orbital motion. We have orbital velocity and orbital period. Again, each of these equations is not on the equation sheet, but very helpful for us to know. So let's talk about our orbital motion here. We know that if a planet or a satellite is in orbit around another planet or a star or whatever it may be, once again, if it's in orbit, assuming that it's a circle, we know that there has to be a centripetal force pulling towards the center of the circle. Well, the only force that exists between these two planets or these two masses is the mutual force of gravity between them. So we know that the centripetal force would once again come from the force of gravity between the two planets. Now the difference is we're not on the surface of the Earth. So rather than using our critical velocity that we used before, we're still going to use mv squared over r for the centripetal force, but now I'm going to use my universal force of gravity, where I'm using g m1 m2 over r squared for the two masses involved. So let's say that this is mass 1, let's say that this is mass 2. R, keep in mind, represents the distance from center to center, which also happens to be the radius of my circular path if it's a perfect circle. So when I look at this equation, a lot of stuff starts to simplify out, right? The mass of the object, which we're calling m1, so the mass of the object in orbit cancels out. One of the distances cancels out, again, because they're representing the same thing. So then I get v squared equals g times the mass of the planet divided by the radius of the planet. And then if I solve, or the radius I should say, of the circular path, not of the planet, but of the circular path that we're going from center to center. And then if I solve the rest of the way, I get the orbital velocity equals the square root of gm over r. Once again, this is a very important equation, not only that we know and that we're able to use, but more importantly, we need to know where this comes from, right? This is not on the equation sheet, and they may ask us to prove or derive this equation. So you need to know where it comes from. It's not too hard. You just have to identify the key relationship for where to start with and then run through it a couple times so that you feel comfortable with it. So that's our orbital velocity. And again, that represents how fast the satellite would be moving as it's in orbit. A couple key concepts that go with this, things to notice, right? One, the mass of the satellite does not come into play for our orbital velocity. So if I have a single mass of, let's say, 1m here, and I have another mass of 2m in the same orbit, they actually should have the exact same orbital velocity. Now keep in mind that doesn't mean everything is the same. The centripetal forces would be different, the momentums would be different, the energies would be different, but it does mean that because they're at the same distance, they have to have the same orbital velocity. And so that's a key relationship that, again, we can see pretty easy if we know where this equation comes from. The second orbital equation that's very helpful is the orbital period, right? And it's basically right on along the same lines of this orbital velocity. So in order to find the orbital period, we actually start with v equals 2 pi r over t, which again we can use anytime we're moving in a circle. And the reason that I'm using this equation is because it helps me then solve for the period, which is t, right? Well, we just found an orbital velocity, so if I take my orbital velocity and plug it in, I get the square root of gm over r equals 2 pi r over t. If I take this equation and rearrange it to solve for t, I would get t equals 2 pi r, so I'm multiplying both sides by t and then dividing by the square root. So I get gm over r. Now obviously that equation would work if we had the radius right there and you could just start plugging stuff in, but we do clean this up typically a little bit more. So 2 pi r times the square root of, because it's on bottom, we would multiply that radical, and then we would bring the r in, make that r squared, which makes it a total of 2 pi times the square root of r cubed all over gm. Once again, a couple concepts that are important to know. R represents the total distance from center to center, right? So that represents the distance from center to center between the objects, and the m used is the mass of whatever we are orbiting around, right? So whatever we're orbiting around, not what's in orbit. So once again, the period does not depend on the satellite at all. It simply depends on what planet or star is it orbiting around and what's the total distance from it. we can see pretty clearly from this equation, if the distance were to get bigger, if the radius between the two were to get bigger, then our period should take longer, right? It should be a longer period for one full cycle, for one full orbit. Okay, so again, these three equations, orbital period, orbital velocity, and going back to the critical velocity, those three equations are three big equations to know, not just the equation. We do not want to memorize the equation, but we want to know where they come from. So that's something you definitely should work on over the next couple days here. The last couple kind of loose ends that I'll tie up, and this isn't by all means everything you need to know about circular motion, but it is a few more key ideas that come into play here. So one, how much work is done when we move in uniform circular motion? So how much work do we do when we're moving in uniform circular motion? Well, the answer to that question, and many of us know, the answer to that question is 0. But it's not just because we're completing one full cycle. I do not have to go all the way around the circle for the work to be 0, right? Even if I just go from here to here, I can prove that the work should be 0 as long as it's uniform circular motion, and as long as this is something like where maybe it's orbit or on a table or what have you, right? And the reason for that is the fact that the force is always pulling towards the center of the circle, and the direction of the velocity or the direction of the motion is always tangent to that. Because those two are perpendicular to each other, the work is perpendicular, the force is perpendicular to the distance, and anytime force is perpendicular to the distance, right, that means that the work is 0. The other way that you could think about work is through energy, right? Work equals a change in energy. Well, if it's uniform circular motion, then the velocity, the speed, is staying the same, and therefore wouldn't 1/2 mv squared, the kinetic energy of the object, also be staying the same? So we can pretty easily prove that the work for circular motion, when it is uniform, should be 0. It's a very key idea. You definitely see this pop up from time to time. If it's not uniform circular motion, the easiest way to find the work done is, again, find that change in energy. So what if it's not uniform? What if it's not a constant speed? Well, maybe I just find the change in either the kinetic or the potential energy as it's going around the circle, right? That's not too hard to do if we take our time with it. And then finally, the last idea that kind of ties in with this stuff as well, mostly with the orbital motion, we have our definition for potential energy. Now we know on Earth potential energy looks something like this, but when I'm talking for orbit, that doesn't make sense for potential energy because gravity is not constant the further I get away from the planet, right? We know right now if I get further from the planet, g gets smaller, right? The acceleration of gravity gets smaller the further away I get. So this equation does not work when we talk orbits. It doesn't make sense. It doesn't fit. So instead, the equation that we reference when we are in orbit, and the good news is this is on our equation sheet, but the equation we use is -g m1 m2 over just a single r. Now, if you don't have calculus, it's tough to prove this equation, but kind of the shortcut, and it's a shortcut, but kind of the shortcut that I remembered is work or energy is force times distance. And if I take the force of gravity, which is gm m1 m2 over r squared, and I multiply it by the distance of r, one of the r's cancels out, and that gives me my representation for work or energy. Again, the tricky part is where does this negative come from? And again, barring some calculus, it's kind of tough to prove that. But we don't need to prove it. We don't necessarily need to know where that comes from for this part, right? But we do need to realize that that represents how to find the potential energy for any type of satellite in orbit. So if they ever ask us what's the total energy or how much potential energy does a satellite have, this is the route to go. Again, the benefit, it's on our equation sheet. We just have to know how to use it. And then finally, the last thing with this section, and I'm going to try to do this on most of these reviews as well, but think about the graphs that would come into play, right, for this. So there's a lot of different graphs you could take. One common one would be maybe an acceleration versus time graph. So if I told you something was moving in uniform circular motion, pretend that's a better circle than it is, but if I asked you to graph the magnitude of the acceleration, if it's uniform circular motion, then shouldn't the centripetal force and the centripetal acceleration be constant the entire time? So if I asked you to graph the acceleration of that, well, it should just be a constant acceleration the whole time. Now the direction would be changing, but if I'm just looking at the magnitude, right, we wouldn't see that on the graph. Another example, a question we've actually seen once or twice before. what happens on maybe a racetrack where I've got straightaways, and then I go around a turn, and then I've got a straightaway, and then I go around a turn, right? So what would that acceleration versus time graph look like? Well, let's assume we're going at a constant speed the whole time. As I go around the turns, I need an acceleration in order to change direction. So from turn to turn, my graph would look, once again, something like a constant acceleration. But once I hit the straightaway, if I'm staying at a constant speed and the direction is not changing, then my velocity does not change, right? So there's no change in velocity. I don't know how I was writing that there. But then if there's no change in velocity, the acceleration should be a constant at 0 for that period of time, right? Once we go into the next turn, we would be accelerating again. And then once we hit the straightaway, we would be at 0 again. So as we can see here, right, the acceleration versus time graph would look something maybe like this piecewise function for circular motion. So as always, think about your graphs. There aren't a ton of graphs that connect to this chapter, but we definitely can tie in some context. Again, this video does not by any means cover everything that we need to know, but hopefully this does give you a chance to overview the circular motion. I would suggest in the next couple days, as you go back through this, I would suggest you try to write down everything that you know from this chapter. And if you need to come back and watch this video again, by all means, feel free to do so.